So I'm Nate Marshak. I'm the Director of Software Engineering for Intel's Data Center Storage Group. If I look uncomfortable up here, it's because I really don't ever wear these types of clothes. Usually I'm in shorts and a t-shirt. So,
I told you don't have to dress up for us.
If I'm kind of moving around a little bit, it's because I'm just not comfortable. Thanks. So, we're going to talk about a couple of, software efforts that we have inside of the data center group. There's a lot of different software things that we do, right? So we're not going to dig into all those different things. We do lots of file system enabling, kernel level drivers, et cetera. But we're going to kind of narrow our focus and kind of dive in on a couple of them here. And that's specifically our Intel Storage Acceleration Library and our Storage Performance Development Kit. So just kind of a quick agenda. We have 20 minutes, so we don't have a whole bunch of slides, but we'll talk briefly about why we're doing it, and then obviously what they are and how it helps, and then just a couple of numbers to look at the end. So you've seen this pretty picture here, right? The pendulum that we've talked about, how our bottlenecks kind of shift between storage, compute, and networking. What we do with these two software entities is we kind of focus in on first maximizing what we provide to our customers. So there's some things that we can do to help them get the most out of the products we provide them. Right, so that's one of the focuses for these two software entities. Again, the bottleneck pendulum. We've talked a lot about 3D XPoint, NVMe, and how that's really changing. Where the bottleneck is in the system. It's interesting when you stop and think, right? Software and operating systems and kernels have been built on the idea that storage is slow, right? So it used to be you would go up to, just kind of an analogy here, someone would say, hey, can you go get me this data? And then I'm going to go off and do something useful for a while, and when you get it, let me know. Well, now that's kind of flipped on its head. Now it's, hey, can you go get me this data? And as you turn, they come back and say, well, here's your data, right? So you have all this locking built into your operating systems, all these, different ways of trying to thread to maximize what you do. And the problem is that is all kind of fundamentally changed now based on the speed of the media. So we're trying to enable the storage transformation, right? So we'll talk real quick about SPDK and then we'll jump into ISA-L. Is anybody familiar with the Data Plane Development Kit?
Nope.
Okay, so DPDK actually is a open source solution that Intel started a while back as part of the comms infrastructure, right? So it was very focused on pulling packets in on a wire and putting them back out on a wire. And we'll talk a little bit about how that's accomplished in the context of SPDK because the concepts are similar, right? We took the concepts being followed for DPDK and we're kind of pushing it into the realm of storage. So we have a few pieces, right? We build on the DPDK. We have a user space, network service TCP/IP stack, and that we'll get into, how this works and what it looks like here in a sec. And then we have a bunch of other user space drivers. The NVMe driver, which we actually open sourced a few weeks ago. Bev Crair announced it at the SDC keynote. There's parts and parcels, so it's a bucket of parts, but you can put it together to actually really drive high-speed IOPS through a system. And then it has kind of a reference software application where we kind of glue ISA-L and SPDK together. Okay, so this is just kind of a high-level picture. There's a lot of different pieces that we're also prototyping and pathfinding with. So this is kind of the stuff that's a little bit more solidified at the moment. So what you see here is a day in the life of a typical bit, right? Data comes in from somewhere in your data center, and this is your storage system actually persisting your data. So the key here is it's all running in user space, right? So from an operating system perspective, right, there's two areas. You have your user space where your applications run, and you have your kernel space where your trusted software runs. And so what we're doing here with SPDK is we're basically running everything in user space. And so the reason why that's important, right, and that's kind of the how it helps part of this. We talked about your operating system kernel having decades and decades of software built into it. Well, a lot of that stuff you don't necessarily need, right, depending on what you're trying to do, but it's still something that you have to traverse through. And a few of the other reasons are you actually spend a lot of time going from user space to kernel space, right? So there's a transition that occurs. You can't just software seamlessly move, execute from one into the other. You have state to save. You have a lot of overhead that you have to do in order to do that safely and reliably. So if you're running everything in user space, you no longer have to do that. The other thing, a few of the other things, the way it's set up is we do polling as opposed to interrupt processing, right? Interrupt processing is something that you have to do for a general purpose system because basically you have to account for all possibilities, right? So you use an interrupt to basically cause your hardware to take action on some stimulus, right? So and that also requires a lot of state to be saved, right? You have to move from your whatever context you're in into that interrupt context. So there's overhead associated with it. And so by running in a pulled mode fashion, you're basically eliminating that overhead. Now, that's not to say that you can't, under certain circumstances, actually decide to stop polling and turn an interrupt on in order to, go into a power savings mode or something like that. But when you have a lot of, heavy traffic going on, the more efficient way to do this is by polling as opposed to through interrupts. It's far more efficient. You also get better cache locality, by doing things in this fashion.
Yeah. So Nate, isn't going polling versus interrupt, isn't there a potential for you to actually lose packets and stuff like that?
No, I mean, so from a polling perspective, the DPDK, actually from an Ethernet perspective, it's 25x faster. Now, obviously with Ethernet, right, you can lose packets, period, right, unless you're doing some sort of TCP/IP. Or some other, data center bridging or something that's going to, guarantee that you get your packets. So, that's really kind of done at a higher level.
Yeah.
Yeah, but Ray was really talking about, aren't you going to have a second packet come in at the port before you've pulled it the first time, and therefore the first packet falls on the floor, not transport loss?
Yeah, so I think when you're looking at the possibility of losing packets, you certainly in a Ethernet fabric you can lose them. But when you're polling, right? So when you're looking at the time it takes to process an interrupt because something's arrived, versus actually just sitting there looking at it, it's far more efficient, and you're less likely to drop
polling in
packets.
user space.
Yeah, you don't go through the kernel at all. Everything gets mapped from.
So what you're really saying is you're polling so fast that...
Not an issue.
Yes, you're less likely to lose packets.
And even though it's in user space, the overall scheduler can't rob you of CPU enough for it to matter?
So you certainly, the prescription is you don't put anything else on that core, right, that you're actually trying to do this work on. because certainly you could, Linux could schedule, or whatever OS could schedule something and kind of get in the way. So you lose, there's a flexibility that goes along with it, right?
Okay.
And this is taking care of placement of which processes go in which core.
Yes.
So does that even include like dedicating which NICs are on which cores for, and
So you're actually getting to the heart of this fourth bullet, right? Removes overhead due to locking. So by basically, polling and setting up, what queues are being processed on which cores, you're removing the need to do general purpose locking, right? Roger got up here and talked a little bit about TSX and, how there's a need for spin locking to keep critical code sections from being, overrun. When you move and kind of turn the picture on its side, and you think about things as opposed to being general purpose, you think about them as being kind of dedicated and focused, you can make some assumptions that make life a lot easier. And doing polling and kind of pinning those things, you get to avoid some of the trouble that goes along with them, with the interrupt model. So in general, the pieces, right, that we have, you have the standard DPDK, which is an Ethernet driver, along with some libraries for memory allocation and really doing things from a high-speed fashion, taking advantage of Intel instructions, to having a user space TCP/IP stack, an iSCSI target, because again, this is really at the moment focused on storage targets, right? Not your compute servers, but a storage target. Now, obviously, when you start talking about hyperconverged, those two things are running on the same system at the same time. And then we have, again, a few kind of what we call back-end drivers, such as our NVM Express user space driver, our CBDMA driver, which Roger also talked about a moment ago, and then a memory driver, which is really just for kind of caching purposes for storage systems that might actually use a DRAM cache. So this one's open source. We're in the process of open sourcing this one, and the rest are things that we provide to our customers directly.
now BSD was mentioned earlier. Was that in terms of this or something else? Just to clarify.
So Roger was talking about FreeBSD in the context of basically, I think it was the NTB driver.
Okay.
So that's a standard
All right.
kernel driver, as opposed to user space kind of different model driver.
Yeah.
But the NVMe user space driver does actually run on FreeBSD. It'll run on both Linux and FreeBSD. We open sourced it a few weeks ago. We had somebody request that we port it, and this one didn't take long to port. Right? Again, POSIX type of simple interfaces. Okay. Any questions? Okay. Okay, so just a quick overview for our Intel Intelligent Storage Acceleration Library. So when you look at SPDK, right, there's kind of it's a framework for building storage applications. This is a library for doing storage type math really fast, right? So ISA-L is focused on, helping customers and other folks in the industry that want to do erasure coding, extremely fast, or deduplication, right, where hashing comes into play, or compression in a fast manner using Intel cores to do that. That's where ISA-L comes in. So it does the math extremely fast, and the way it does that is, yes, we're using our assembly level instructions, but we also have the privilege of knowing actually how the CPU is architected, right? So we know a bit more about the internals of the CPU, so we can actually do some further tuning and tweaking to best take use of it.
Right, so first of all, you're taking advantage of everything that's in the latest microcode that might not have made it into the Microsoft C compiler yet.
Yeah.
And then you go, well, I could do it in this one instruction that takes 20 cycles, or these two instructions that take 5 each.
Yes.
Okay.
Yeah, and we have an understanding for actually the architecture of the CPU, so we know if I do 3 of these back to back based on the way the CPU is constructed, it's going to be more efficient than trying to do them one at a time.
So you're even digging down into how it pipelines. And,
Yep,
yeah.
exactly.
So is the SPDK and this library, are they generally available to any organization that wants them, or are they licensed? Or
So we give them away freely with a license. Pieces of them are open sourced, right? So the erasure coding piece of ISA-L is open source. It's actually in use in things like Ceph, and it's being similar things being done with Swift, right? So there's a lot in other places as well, and we're looking to open source more, especially in the context of ISA-L. So in general, that's kind of the push is towards being open as much as we can. It runs on, so ISA-L is tested and executed on Linux, FreeBSD, Mac OS, and Windows Server. And then obviously, right, it actually, one of the key points here is it'll run on both our Intel Xeon and our Intel Atom processors. And it's tuned, again, in a similar fashion. Okay, so let's real quick kind of talk a little bit about, what's inside of ISA-L. What are some of the functionalities that it provides you, as a consumer? So data protection, right? So it'll do things like RAID 5, RAID 6, the algorithms for those things, and erasure code in an extremely fast way, right? Again, it's highly tuned, hand coded assembly specific to our processors. Data integrity. So there's various instructions in our chips that kind of focus on this, CRC, T10, etc. And so we have functions built in for doing those in a very high speed fashion. Cryptographic hashing. So this comes into play in a lot of different cases. Obviously, for storage, one of the big ones is deduplication, right? You need to use hashing in order to understand when you have a 1 megabyte chunk that it's the same as this other 1 megabyte chunk over here. Compression, obviously that's a big deal when it comes to storage. Roger, talked a little bit about QAT, our Quick Assist technology, which is a offload engine. We have similar types of solutions that actually use the IA cores to provide compression. And
the library auto detects the offload, so I can have one.
So that's something that we're working on right now.
Okay, yeah, because I want one piece of code that.
Yep, totally agree. Yep. And then encryption, obviously, we kind of list out some of the various instructions that we use, but we provide encryption services through ISA-L as well. Okay, so this is the last slide. Just throwing out a few different numbers. We have tables and tables of numbers that we could provide, but I know I don't want to take up too much of your time with that. But with SPDK, right, when we compare ourselves to Linux LIO, which is the in-kernel SCSI target stack, we see 7x improvement in IOPS. And again, all this is really kind of focused on driving down the overhead of software so that we can maximize the abilities of our next-gen non-volatile memory. 10x fewer cores, or 10x as fast, as whatever you want to look at it, for the NVMe driver that's running in user space versus the one that's running in the Linux kernel. And then again, for ISA-L, 8x bandwidth on hashing versus OpenSSL, 5x bandwidth for compression versus zlib.
Now, not to get off topic, but are you seeing companies or developers use ISA-L for non-storage things, just like standard security acceleration or?
So typically not. Now, Intel as a company, we actually have a variety of different programs. ISA-L is just one of them. There's, the IPP team inside of SSG, and then, there's a handful of other groups that actually provide tailored
Corresponding libraries or type functionality for
Exactly.
different uses. Okay.
But we do actually sync regularly, talk regularly to see whether there's some overlap between those things where one can be helping the other.
Okay.